Thank you. Good afternoon. I wanted to begin my presentation with an association exercise. So I have here two words, nature, or you can think of it as biology, and computers, or you can think of it as technology if you want. And I want to associate some images and some words with those terms. So first we have a picture here, lots of different creatures. Pretty clearly, that's an example of what we see in nature. And this is a rack of computer servers, so this is what we get for computer technology. If we think about the word adapt, that's nature, right? Nature is very adaptable. Fixed. So computers, once you have a piece of hardware, it tends to be fixed. Variety. We see lots of variety in nature. Imagine a forest of trees. Those trees may all be the same species, but each one individually is different. So even within the same sets of trees, the same species, we get lots of variety. And in contrast, computers tend to be repetitive and identical. So if you have a problem, a task that you want done over and over and over again in exactly the same way, you give it to a computer to do. Nature learns. You can teach a dog, even an old dog it turns out, new tricks. Whereas computers tend to repeat the same mistakes over and over and over again. So why this dichotomy between what we see in nature and biology versus what we see with computers and technology? Well, a big part of the reason for that difference is that things in nature evolve and computers are programmed. And so this raises an interesting question, which is what if we could sort of break that rule and allow computers to evolve? Seems like sort of a strange question, and to address it we have to think a little bit about, well, what really is evolution? And we can think of evolution as a process with four major components. So the first component is a population. Imagine, if you will, a population of rabbits. And within that population of rabbits, we have lots of variation. So there are faster rabbits and slower rabbits. There are rabbits that are more camouflaged and blend in better because of their colors, and rabbits that stand out more. So we have variation. And then based on that variation, we have selection, the classic sort of survival of the fittest. Right? The faster rabbits are better at escaping the foxes. And what that leads to then, because they can survive, is inheritance. So those rabbits that escape the foxes, either by being faster or being more camouflaged, get to reproduce and pass their genes on to their offspring. So these four components are what makes up the process of evolution. And the question becomes, can we apply these to computers and computer technology? And I want to begin with an example that I suspect everybody is pretty familiar with, which is video games. And you may be thinking, wait, video games? Why video games? Well, in order to answer that question, we have to sort of use an example of a video game. So this is a video game called Darwin's Demons, and you can see it's sort of a classic shooter-type arcade game, right? We've got a whole bunch of aliens, and the player is flying a ship and shooting at them. And so how does this relate to evolution? Well, if we think of those four components, we have a population here. We have a population of opponents, of aliens. And within that population, you can see there's already a lot of variation. Some of them look a little bit different, they move differently, so their behavior is different. They may shoot more rapidly or shoot slower. They may charge the player or hang out in the corners. And this is pretty true of all video games, right? Rarely in this kind of video game do you have to face the same opponent over and over again. That would get boring. So instead we put in variation. And so in terms of the components of evolution, we already have two of them, a population and variation. And then the third one was selection. So we might ask, well, is selection taking place here? And if so, where? And the answer is yes. That's the player's job, right? They're shooting at the aliens. They're doing the selection. And we can go a little further and say we're going to, in terms of fitness, say aliens that survive longer or shoot more or charge the bottom of the screen get better fitness. So we have already 3 of the 4 components we need for evolution. We have our population, we have variation, we have selection. What we're missing is inheritance. So here's 2 of our opponents, 2 of our aliens from the game, and you can see they have variation, so they look different. Their eyes are different colored, they have a different shape. If we were to put them back into the game, we could see that they behave differently. Maybe they move differently, or they shoot at different rates, or different types of bullets. So we have all of that variation. Well, it turns out, of course, because they're computer-generated aliens, all of those things are really just controlled by their code, which is a bunch of numbers. And so we can think of the numbers that define how they look and how they behave as their digital DNA. And so now that we've said the way these creatures, these aliens, these opponents in our video game look and behave is based on this digital DNA, now we can put in inheritance. We can say, okay, the aliens that last the longest or shoot the best are the ones that get to reproduce, and they get to take their digital DNA and combine it and pass it on to create a new alien. And we can even, if we want, throw in mutation and put in some random variation as well. And so now we have all of the components of evolution put into, in this case, a video game. So what happens when you do this? Well, you end up with a video game that starts by looking like this. And after you've played it for a while, it looks like this. And you can see the aliens have evolved to shoot faster. There's all sorts of different patterns, different strategies that they've adopted. And this isn't limited to just sort of our simple arcade-style game and simple creatures. We can have much more complicated creatures in our games. So here's an example of a 3D monster that we could put into a game, and you'll notice that it's changing. It has a digital DNA that controls things like how long its legs are, or what color it is, or how long its tail or its tentacles are. And this is, again, all controlled by a series of numbers. It's digital DNA. And in this case, we're sort of showing random mutations, so you can see the variety that can come from it. Nor is this idea limited to just video games. So NASA has used these same sorts of evolutionary techniques to actually evolve antennas that they use on satellites. And the idea there is you have a population of satellite designs, and a population of antenna designs, and each antenna gets a fitness based on how well it does its task. There are companies that choose stock portfolios and mutual fund mixes using an evolutionary technique in which fitness is based on the risk and the reward for that particular combination of stocks. There are researchers who are applying evolutionary techniques to music. And so the digital DNA for music is basically the musical score, and the fitness is how good that piece of music sounds. And the better pieces of music get selected and get to mix their digital DNA to create new pieces of music. It can also be applied to things like robot design and robot behaviors. So just like we can see the virtual creatures in our games change, we can actually see physical robots change, and many more applications of this idea of evolution. And so we might ask, what can we expect in the future? And one possibility that we should be thinking about is that we have computers that can adapt and learn and, most of all, evolve. Thank you.